Alright, for the PID controller, it is just as simple as the proportional control, which is the error, and then plus the 1 over tau I s, which is the integral control, and then plus the tau d s, which is the derivation control. Now it's pretty simple. So to write the transfer function, all we have to do is just some basic algebra, and it is you want to take the I guess you have to do so all of these are actually errors, so I need to have an error sign there, which means we can take an e out, and then we can make a common factor of tau is, so it'll just be kce over 1 plus tau d s squared tau I over tau is. Actually, I'm still wrong a little bit. It's supposed to be tau is. And then you have your final proportional PID controller transfer function.
Alright, so we're returning today with part B of the homework, which is going to be a little long just because of how many parts there are. There's like 8 parts, I think. 7. That's close enough. Alright. So to start this, we're going to start by multiplying some transfer functions and converting them to polynomials and whatnot, which is what you're supposed to do in this. This is just going to be the basic initial setup. So I have imported here all of the stuff that we're going to need. NumPy, JAX, Plotly, SciPy. I don't think we actually have solve IVP here because we're trying to hard code the solve IVP still. And then we've got polynomial functions and transfer functions, which we are going to get into now. So first I need to make a series of polynomials and functions that need to multiply by each other, so I'm going to show you how that works. And so we're going to start out with a transfer function to a polynomial, and that's going to be with respect to one transfer function, and we're just going to simply return transfer function numerator. Well, I know what I did wrong. I need to start with this p. This p function here is going to multiply the polynomials together. Yep. So you just find the coefficients, and then you get the numerator is going to be transfer function dot num, and that is going to flip. Once you eventually do this, you're going to try to flip, because how do I explain this? So the best way, so when you put out a polynomial, let me put in a little code here, p, and then just do p 1, 2, 3, 4. Rather 1, 2, 2, and then 3. Let's say Shift Enter. What? Alright. I actually need to put these in brackets. Stop. So this is what a polynomial function looks like. So 1x plus 2x, blah, blah, blah. The transfer function has these coefficients in the same order, or sorry, it'll be the same, but it is in descending order, so you would start with 3 to get to a transfer function. And that's what I'm trying to do here, is to just multiply these transfer functions. And that's going to be how you flip these, is the -1. So you rip everything, and then you just, it's -1. So you flip it. And then, well, alright. And we need to define another function, which is going to be polynomials to the transfer function, and that's going to be with respect to a numerator and a denominator. And then you need to return this transfer function in dot coefficient. It's going to be the same thing here. Yep, those work. Then you need to define a multiplication, two transfer functions, so TF1 and TF2, not period, comma. And then it's going to be TF, and then it's going to be N1 D1 equals TF2 polynomial TF1, and then this will just be the second transfer function, and then return polynomial to transfer function n1 times d1 and n2 times d2. So you get your fractions. That's still working, at least seems. So then another function will be the feedback loop that we had derived. And that's going to be with the transfer function, two different transfer functions, TFB and with two different transfer functions, it's going to be TFF and TFB. So NF and DF are going to be equal to the transfer function to polynomial for TFF. And then NB and DB are going to be equal to this, but with TFB. Then return the P to TF function. Then return the P to, and then return this again to this is going to be NB. This is going to be NF times DB, and then DF DB plus NF And then we need one more transfer function, and that's going to be the PID. And we already have derived that, so it's going to be KC tau I and tau D. And then we get a return KC, no. Tau I, KC tau I, and tau D, KC tau I, KC by itself, and then I believe this is the error, but it's tau I, and then rho. We're not going to do too much with these, but this is just to show how this thing works. The real problem is what we get into now. Alright, so I don't have a whiteboard, but I do have this right here. So this is the block diagram for the problem we're about to do. Probably should sit right here. Okay, so we start with our initial flow rate Q1. We pass that through this transfer function block, which is the R1 over A1 R1S plus 1, and then that spits out the first height of the first tank, and then we do the 1 over R1 to spit out the flow rate for out of that tank, which is Q2, and then that goes into the next transfer function for to spit out the height. And then we have a measurement device which multiplies that height by 1, because it's pretty simple right now. We're not trying to like unit convert or anything. And then it spits that height back out, and then it goes in through a set point control device, which is this circle here. It adds the set point and subtracts what height 2 is at, and this H2SP minus H spits the error calculation out, and then that goes through the PID controller, which we derived the equation for that transfer function already, which spits out the corrected flow rate, and we loop it back again. Now we could alternatively spit this H2 out and then go to 1 over R2, and then that would spit out the Q3, the flow rate out of tank 2, which actually I should scooch this over so you can see that. But we don't want to do that in this case. We could, and then we could put it through a measurement device if that was what the parameter we cared about. We could also stop this at any point for any parameter we cared about and continue to add them for tanks. But this is kind of the process that the computer has to go through in order to make an entire feedback loop control. Alright, so that block diagram I just showed, we're actually going to simplify that quite nicely. So we have the same H2, we have the same H2 set point. We have the, let's see, you can see this, plus and minus, and we simplify all the measurement devices, or rather all the control devices to GC, all the process devices to GP, and then feedback and all the measurement devices are GM, and then we have our feedback loop. And then we want to go over this this function right here, I believe, the entire servo function. So we got to start by, this spits out the overall height here, and then the height does also return to that function. So then we get, I'm trying to find the camera and I'm not able to. So then we get the H2 set point minus H minus the HGM times GC and GP is equal to H. And then we also have, once you multiply that out, that's HSP, the set point control and process, minus the H, the height, measurement, control, and process. And that is again equal to H, and you want to get some common factors. So we algebra that out to be the overall height is equal to the set point times GC GP over 1 plus GM GC and GP. And that is our overall servo function for the process, and we can use that now to go back then and code everything. So yeah, we're ready for all part 2 now. All right, I'm gonna start. I gotta put down these different parts that we derived. So we've got A1 is equal to 1. We've got R1 is equal to 2. We've got A2 is also equal to 1. And we've got R2 is also equal to 2. Then we have to have this QC to H2, or sorry, QC to a Q2. And that's going to be equal to the transfer function of like 1 over A1 R1 and then 1 and then we're going to have a very similar Q2 to H2, these two transfer functions. And now it's going to be equal to the same thing almost, but this is going to be R2 over A2 R2, and then also 1. So those are our variables, and now we have to set up a random number, might as well put it here, a random number generator, and that's going to be equal to numpy.random state, and it's just going to be equal to 1 2 3. So now we get to the meat of the code. And that is, you got to make an expected time, and that's going to be equal to numpy linspace from 0 to 15 with 50 points. Then we want our transfer function for the process is I'm just going to say TFP is equal to TF mult I don't remember when I need to capitalize these, so transfer multiplication, which is the one that we derived up here. And it's it's going to be these two variables. So QC, Q2, and Q2H2. And I did it wrong.
Alright, so I'm back, and I figured out what I did wrong. It was up here. The only thing I did was I forgot to add this p here. So I forgot to turn it into a polynomial. Now, I can continue because I got everything working. And I also did figure out these were also wrong. I had N1, D1, and N2, D2, which is supposed to be this now. And these are the forward and backward reactions. We'll get to those later though. Alright, so the next thing that I have to do is fill in a blank variable since we've already got the TF process. So we need an underscore and an H2 expected. And set those equal to the TFP, make it a step function, and set the time equal to the T expected. And let's see if that works. Alright, so the next step, is to actually turn, because if we just did this now, this H2 XP, this expected height would be just a very clean line of data. So we want to make this, we're synthesizing data here. So H2 EXP is equal to RNG dot normal. Location equals H2 EXP scale equals 0.02. And then we just have to plot it up. Come on, it's popping up. I think I need to put this in the markers mode because it's not supposed to look like that. Crap. Alright. There we go. That's a more good-looking data set. For the next part of this, we're going to need to do a first order plus time delay. So here we go. And have this with some respect to some random vector. And that vector is going to be equal to k, tau, and theta. Are equal to vector. We gotta make an equation of y is equal to k times 1 minus the e to the negative theta to the negative t expected minus theta over tau. And then we want to return a Jax-Numpy where function. And this is going to set something true and false, kind of, sort of, where TEXP is greater than theta. So we don't have an x, and then we want y to equal y.
I got that first part. And then we need to set up a guess for the vector. It's going to be 2, 4, and 1 for our first guess. We'll see why in a minute. And then I need to define another function. Alright, so I did get a little bit ahead of myself in that last video where I started making this. This is actually for part C. So what I need to start out is with these 3 values here, like on the homework. I should them right around this step right here, and then I need to simulate the response of the transfer step function, so we'll get to that real quick. So first, I need to say the t forward is equal to, as long as it's the same one here that I did up there, tf forward is equal to, it should be tf multiplication, and it should be the PID part, and that's going to be kc tau I and tau d, and then another tf multiplication, and then it's going to be the qc q2 and then q2h2. Let's see, that should work. Oh boy, yay. Okay, I actually got the, this is supposed to go here, and then it should be this to close it off. And it still doesn't work. So the TF feedback is going to be equal to, so TF feed, where we have the forward transfer function, and then TF, and it should be ones from both of those. So we got 1, 1, and then we just got to plot it up. Boolean space from 0 to 100 with 500 data points, and then t plot and height 2 are going to be equal to the step function of t b feedback. Well, TBF, it's transfer function feedback. Then t equals t plot, and did I do dot step? I think I did. Alright. And that means, well, then we plot it up, so figure equals make sub x equals t plot, y equals h2, come on, and then mode equals lines. It's broken because this is broken. after a long process of deliberation, I actually finally found out I just forgot to actually turn this into a transfer function. It was very painful. So yeah, this is, I don't know if this is right, but this is supposedly the response of the system with all of these things here. And I remember in the video I was watching it was like 10, so look and see what that kind of thing does. Okay, so I am doing it right. This is just 0.8. Alright. Now, I do believe this is supposed to go above, but we have part B done, so this is what I have to figure out for the next time. Alright, I'm back again. I kind of thought I was done, but I was not. So I have one more part to add to this. So I need to simulate, I need to do basically this entire thing here, but superimpose another plot on top of it. Something similar to it anyways. So we're going to start with a simulated time. That's going to be numpy linspace. And then from 0 to, let's give it 10, and then with 500 little thingies in between. We've got to set then our omega equal to 1, which is a frequency. Then we have to have an error, which is a cosine signal, so numpy cosine. Then multiply our frequency by our time simulation. And then it should be as simple as nope. We're gonna have two scatters here. But I need to what are you? No. Advertise. I didn't even click on advertisements. Alright. These are going to be both the simulated time. This is going to be, yep, this is still going to be H2, but this is going to be error. And okay, do we see if I can do it on the same? Hey, I did do it, except it doesn't look quite right. It should not taper off like that. It should be more of a cosine. So let's see what I did wrong here. So first, I actually do have to make and store a variable I don't care about. So this, and then H2. And set that equal to this signal function. And then I need the TF. I need the forward transfer function. I need E, and I need our simulation time. That should be. Of course, I didn't do it right. Underscore. There we go. So that is what the error and the height kind of looks like superimposed. So this just means I gotta name you input. Output. Alright, so the output is the error, and notice that they're always going to be just about opposite of each other, and that's because the error is trying to correct for that height. So that's when that happens. We can put our simulation time out to here, and then see that it just keeps constantly oscillating like this, where the error and the height are always at odds, and then they do meet. So the error and the odds right at the same, oh, the error and the height. So that's then completing this part 2. And I can also show how with changing this to like a much more stable system. Whoa, that is not at all stable. It's probably because I screwed with the height here, honestly. Yeah, I screwed with the height. There we go. So if I just run those two freshly, then you can see that it goes straight to 1, and that is a more stable system with a higher integral control. Now I'm actually curious what happens if you have a derivative control. Makes it even smoother. Okay, no hiccups there. But if you raise Kc and lower tau I, you get some very, very disturbing results in oscillations here. And that'll be it for this part.